Welcome to the Precharge overview for Waterloo Forming Electric. Um, we will be going over today precharging of high voltage systems and how we used to implement it on our Waterloo Forming Electric vehicle. Currently, uh, the system on our 2022 vehicle and going forward does not use this system. It uses a multi-step precharge system to deal with the parasitic loads on our high voltage bus, but I think this is a good document and presentation for general precharging and how it works. So we'll begin. What is precharge? So when we're talking about precharge, we're talking about the connection of our internal high voltage power in the pack to our high voltage loads. So we have essentially a high voltage battery of 300 volts, and we want to connect it to our loads. By precharging, what we mean is rather than instantaneously applying this voltage to the high voltage bus, we're going to steadily increase the voltage to prevent certain undesired behavior. So this is an example of an instantaneous application of the high voltage onto the high voltage bus. This is what would happen, but this is not ideal, and I will explain this in a minute. This is a depiction of a typical precharge process. You can see the voltage over time steadily increases. So why do we need to precharge? When we're dealing with stuff like motor controllers, they have a tremendous amount of capacitance. So in total on our high voltage bus for Waterloo Forming Electric vehicle, we have about 1.3 millifarads of capacitance, which is very high. And to explain why this is an issue, let's just look at the simple differential equation for a capacitor. Essentially, the current is equal to our capacitance multiplied by dV over dt. So we have our very high capacitance, 1.3 millifarads is very high. Typically, when we refer to capacitance, we're referring it to in the pico, nano, and microfarad range. And we also have a very high dV over dt. So if we were to instantaneously apply the voltage, you would see here our dV over dt is very high, nearly infinite. So that would produce a nearly infinite instantaneous current, which is very bad. That can cause tremendous strain on our high voltage bus. It can pop our fuses, and it can break multiple components along the way. So our high voltage components actually are rated for tremendous amounts of current, hundreds of amps, but we do not want to be doing that. And if we do not properly precharge, we could be seeing kiloamps. So we have our limits, and we should play within them. A big source of concern when we're talking about high currents on our bus is our contactors. So contactors are essentially these large electronically controlled switches which connect the power in our pack to our power on our HV bus. They are effectively high voltage, high current relays. If too much current passes through these contactors, they will heat up and the metal will actually melt and weld them. So if there's a lot of current going through this contactor, the connection point will weld and it will be impossible to open the contactors. This is very dangerous because our contactors essentially isolate our high voltage within our vehicle. It keeps it in the battery away from our loads when we don't want to be powering our loads. So if the contactors were to get welded shut, then we would not be able to isolate our high voltage battery from our loads without pulling the HVD or interrupting some other source of along the path. So if we were welded contactors, it would be very bad, as we might not even know it, but high voltage would be applied through the motor controllers, and if someone were to go work on those, there could be a potential for danger. All right. So this is a top level view of our accumulator. I'll go through a little bit of how it's laid out. I won't go through every component, but here we have our positive side with this little connector here that connects to our battery. So the positive side, we have our tractive system fuse, TS fuse. That's on our positive side. It goes, the positive 300 volts will pass through this bus bar, and then we have something called an air plus, which is accumulator isolation relay. So it is our contactor. I will be referring to them as contactors through the rest of this presentation. So we have our positive contactor, which we will open and close to isolate our high voltage battery energy from our high voltage loads. So we open them up and it will not be powering our loads. We pass through here to our actual high voltage loads through our positive connector. They go through the positive connector to the negative connector, back through, and we have our negative air, which is our negative side contactor, and it goes back into the negative side of the battery. And mounted on the lid here, which we'll get into in a second, is our PC-DC resistor, which stands for precharge or discharge resistor. This is a more high-level view, so we have our positive connector, HVD, positive contactor, our actual batteries, our segments, go back through our negative contactor, back through our negative connector. So this is a diagram of our entire precharge discharge system. We actually have, I forgot to mention here, our precharge path. So I will not try and explain on this. I'll try and explain on this diagram, but I think it is best to go straight into it. But this is effectively how it works. We have a connector here to our relay, our PC-DC relay, which switches one side of the precharge resistor. The precharge resistor has one side connected to our positive connector here. When it's in our discharge mode, the resistor is connected between our positive connector through here to the negative connector. So the resistor is in parallel with our pack essentially. When we're in precharge mode, the resistor has one side on the positive connector, and the resistor goes through and connects to the other side of the contactor here. So our precharge process has 5 steps. Most teams, from my understanding, only use 1 or 2 steps, but we perform a bunch of self-sanity checks to ensure we don't have all the contactors and make sure before we are precharging, everything is safe and nothing is out of the ordinary and going to potentially damage our system. So step 1 of our precharge system is we have our high voltage battery, 300 volts, and our positive contactor is open, our negative contactor is open, and our PC-DC resistor is in discharge mode. So you can see we have 1 kilo ohms and it's completely across our high voltage load, our 1.348 millifarad capacitor. So in this situation, nothing's happening. Our capacitor is discharged as there's a resistor in parallel with it and no current is flowing. We perform a bunch of checks here, which I won't go over, but we just make sure contactors aren't welded. The next step is we want to switch to precharge. So we move our PC-DC resistor from discharge mode into precharge mode. So we attach our resistor across our positive contactor. Our contactors are still open, but we just move the PC-DC relay to get it in that situation. Perform a bunch of checks here to make sure everything is good and our measurements are good. We have a bunch of ADCs at each point to check, run sanity checks and make sure the connections are proper. Step 3, we put our discharge, we put the resistor back in discharge mode, so it's across our high voltage load, and we close our negative contactor. Still, nothing is occurring. We're just performing checks. No current can flow here. Our final step is to begin precharge. So we move our resistor from across our high voltage load to across our positive contactor. And you can see here now we have a path from our high voltage battery through to our high voltage load. There's a solid current path. And effectively what we've created is an RC filter, an RC charging circuit. So I ran an LT-Spice simulation using these simple parameters, and this is the precharge system we get. We have a little bit of a current spike here because instantaneously we're applying voltage to the capacitor, though not a tremendous amount as we have our current limiting resistor. So we have a little spike of current and then it decays over time as the capacitor charges up. And we also have our voltage on our high voltage bus steadily increasing. So we don't surpass 300 milliamps, which is very good. And we slowly precharge our high voltage bus. And along the way, we perform checks, and we go on to the next step when our bus voltage is greater than 90% of our battery voltage. So the final step here, which you can see, is it's maybe a little bit confusing, but I'll go over it. We close both contactors. So when we close both contactors, effectively what we do is we're adding 200 milliohms, or effectively 0 ohms, in these two positions. So we're closing the circuit, and now this 1 kilo ohm resistor is effectively useless, and we just have a solid path across our capacitor. This is going to induce a little bit of inrush current because we're moving this 1 kilo ohm resistor, and our capacitors are technically never fully charged, but it's a very small amount of impulse current. So you can see here, when we close, if we start 285 volts, we close the contactor, we actually get quite a large spike in current. But as we close at higher contactor bus voltages, so at 285 volts, we get 70 amps of inrush current, quite a bit. At 295 volts, we get 26 amps, which is like quite a bit, but it's also for a very, very small time scale, as you can see, very small. It decays to 0 amps in 4 milliseconds. And that is our precharge process. Our discharge process is a lot simpler. Essentially, all we do is open both contactors and set our PC-DC relay to discharge. So in this situation, when our capacitor is fully charged, it will discharge across this resistor until 0 volts is on our high voltage bus. There's a little bit of a story here. I will not be going over it. But one thing we have learned in our workings at Formula Electric is when we're dealing with high voltage systems, there are a lot of things you can't predict. So parasitic loads on our high voltage bus was an issue we experienced, and there are many solutions to this. One of them is to create a DC-DC, so active recharging our high voltage bus. We did not go with that method. We went with multi-step precharge, which we have found to be very effective and a lot simpler method for handling that situation. Thank you for watching. This is on the Waterloo Formula Electric Confluence page. We have a Confluence page called Precharge Overview. Thank you very much.